In this video, I'm going to ask how fatty acid breakdown and fatty acid production are coordinated with one another. This is actually the fourth video that I've done in a series looking at fats as metabolic fuel. So you might want to check out previous videos to give you context for this one. But if you feel like you already know enough about how fatty acid breakdown and oxidation work, let's just jump into this. So the question, how are fatty acid production and breakdown coordinated with one another? And I'd actually like to set this up by looking at something that I've looked at in previous videos, which is glycogen production and breakdown. Because it turns out glycogen production and breakdown and fatty acid production and breakdown parallel one another really nicely. So if we look at a physiological level, if we consider a low blood sugar state, what we see is something like the following happening. So in muscle cells and myocytes, we are consuming glucose, we are consuming fats, and we are burning those to do whatever cool thing that we're doing, even if that's just sitting there while our blood glucose is low. The pancreas is signaling blood sugar is low by dumping out the hormone glucagon. And what this is triggering in liver cells is the breakdown of glycogen into glucose. So glucose subunits are being pulled out of glucose, or glycogen, sorry, being dumped into the bloodstream. And then inside of adipocytes, inside of fat cells, triglycerides are being broken down into fatty acids and then also dumped into the bloodstream. So we're seeing a parallel behavior, right? In a low blood sugar condition, we're seeing glycogen being broken down to form its subunits, and we're seeing triglycerides being formed into fatty acids. And then inside of the muscle myocyte cell, we're actually going to see fatty acids being broken down into their subunits, being broken down as acetyl-CoA, right? So running in parallel, both of them are moving in the same direction. We see something similar in a high blood sugar scenario. So under this scenario, what we're seeing is glucose is being imported by myocytes, by muscle cells, and stored as glucose, as glycogen. The pancreas is signaling, hey, blood sugar is high, and it's dumping out insulin. This is causing liver cells to import glucose and store that as glycogen, so they're making more glycogen, but also to store this glucose as fat and then produce triglycerides that can then be imported into adipocytes. Likewise, adipocytes are importing glucose to turn it into fats and fatty acids. And okay, there's a lot of moving parts there, but hopefully what you can see is, again, we're seeing a parallel flow, that the glucose is going into glycogen and fats are going into being stored as more fats, and glucose is being stored as fat. So the question is, how do we achieve this regulation, this coordinate regulation between these two pathways biochemically? And the reason I'm starting there is because we've already answered some of this coordinate regulation question for glycogen in previous videos. So what I've showed in the past is, or what I've described in the past, is how phosphorylation can reciprocally regulate glycogen production and breakdown. So glycogen synthase, when it is dephosphorylated, is active, and what that says is store energy for later. So if blood sugar is high, this is going to be saying make glycogen out of glucose. If it is phosphorylated, it is now in the off state and it is no longer synthesizing glucose. Or sorry, synthesizing glycogen from glucose. The pair enzyme, this glycogen phosphorylase, is inactive in the dephosphorylated form, but in the phosphorylated form, it is active. And what it's doing is it's breaking down glycogen and turning it into glucose. It's saying release glucose energy use to use now. So there's this switch going on. I'll bring myself back. There's this switch, right? It's a global switch from being, if we're unphosphorylated, we are in a store glucose as glycogen state. And then when we phosphorylate, it flips the switch over, and now we are in a breakdown glycogen and form glucose state, right? So phosphorylation is driving this global switch. It's like this big breaker that's flipping, switching the system from one behavior to the other. This is triggered in a coordinated fashion using upstream signaling hormones. Now, I'm not going to go into the details of this. I've done it in a previous video if you're interested. But basically, glucagon up here, low blood sugar, sends down this big cascade of activations and whatever else, and it triggers that phosphorylation of the glycogen phosphorylase that causes the breakdown of glucose and its release. Whereas insulin, the high blood sugar hormone, does the same thing over here, complicated process. But what it does is it switches the switch the other direction. It dephosphorylates it, saying store glucose as glycogen, right? So there's coordinated switching because of this coordinated phosphorylation that's plugged into glucagon and insulin signaling. Okay, so hopefully that is ringing some bells, reminding you of some things we've talked about. Turns out fatty acid production and breakdown are also reciprocally regulated. So let's dig into that mechanism. Now, one of the key points here is that that's important to this regulation is that beta oxidation occurs in the mitochondrial matrix, whereas fatty acid synthesis occurs in the cytosol. So they're actually occurring in two different compartments. And it turns out that this separation into two compartments is key for how these pathways are coordinated. Okay, so let's think about the possible things that can happen to an acyl-CoA. So this is a fatty acid that has the coenzyme A on it. It's been imported. It's inside of the cell. Maybe it was synthesized by the cell. Somehow it's in the cell. One of the things that can happen to it is it can be imported by the carnitine shuttle into the mitochondria, and then it can undergo beta oxidation, right? So this is one fate. The other fate is that acyl-CoA can be synthesized from acetyl-CoA. So we can be making acyl-CoA and then ultimately, if we're a liver cell, exporting it as triglycerides, right? So option one, the acetyl-CoA is burned. Option two, it's being exported as triglycerides. And there's really, these are the two possible ways we can think about it. We are either making it or we are breaking it down. The question is, how do we avoid doing both of these at the same time, right? If we imagine a hypothetical cell that is cranking along, making acyl-CoAs, and then immediately burning them by beta oxidation, that would be extraordinarily energetically expensive. We'd be wasting energy effectively, and so cells really try to avoid running both of these full power at the same time. So let's start adding regulatory levels to this scheme. So first, high citrate levels, which are an indicator of high energy, activate malonyl-CoA production. And in case you're wondering why high citrate levels are an indicator of high energy, think about the citric acid cycle. If you're continually feeding into that, citrate is one of the first steps. So it's a good indicator that basically things are full up, things are running at full speed. So citrate activates malonyl-CoA production. So if energy levels are high, it's saying make malonyl-CoA. And this makes sense, right? If energy levels are high, making fats is a pretty reasonable thing to start doing. You're going to start investing energy to store fats. It costs energy to make fat more than you even get out, but you're storing that fat, that energy for later because your energy is high right now. So citrate levels turn on malonyl-CoA production. But then malonyl-CoA inhibits beta oxidation. What it comes is, you can see this thing come down here, it inhibits that arrow. And what it's actually doing is it's inhibiting beta oxidation by inhibiting the carnitine shuttle. In fact, it inhibits this molecule here, the carnitine palmitoyl transferase 1. That's the rate-limiting step for moving acyl-CoA into mitochondria. By inhibiting the carnitine shuttle, basically it can totally shut off beta oxidation. You can't move the molecule into the matrix. You can't do beta oxidation. Okay, and so what that means is that in this state, I'm going to actually go back. That's a confusing graphic. So malonyl-CoA is inhibiting beta oxidation by inhibiting import of acyl-CoA into the mitochondria. Great. Now let's think about the opposite. So first, let's imagine that our citrate concentrations go down. So we're no longer in a super high energy state for the cell, but we're continually, that means we're starting to build up our acyl-CoA. So we're making acyl-CoA, but we're not exporting it as triglycerides. There's some other signals that are involved in that export process. So acyl-CoA concentrations are starting to build up. What happens then? Well, now it starts inhibiting its own formation. This is a phenomenon known as product inhibition. So the acyl-CoA is inhibiting this enzyme, acetyl-CoA carboxylase. So it's preventing formation of malonyl-CoA. This then relieves inhibition of the shuttle, right? This molecule concentration is going to start going down because this concentration has been going up and we're inhibiting here. We relieve that inhibition and we activate beta oxidation. So cellular energy levels are low, So what does a cell want to do? It wants to start burning, this is a liver cell, it wants to start burning acyl-CoA as for beta oxidation. So it flips over and starts turning that process on. And it does so because you're no longer inhibiting the carnitine shuttle. And so what we see here is this reciprocal regulation. Now I've just drawn all the arrows on with the whole thing intact. What we can see here is that citrate activates malonyl-CoA production. So if energy levels are high, you're producing malonyl-CoA. That's inhibiting breaking down the acyl-CoA by beta oxidation, which means you're going to take your acyl-CoAs and you're going to export them as fats. In contrast, if you have a high concentration of acyl-CoA, either because you've made enough or because you've imported a bunch of it, what that's going to do is it's going to inhibit formation of malonyl-CoA. That's going to relieve the inhibition of the carnitine shuttle and ultimately let you run beta oxidation. Last thing I want to point out about this is you may have noticed if you were paying attention, like, oh, there's an open circle there in a process diagram that tells us that this enzyme can be modified in some way. Turns out this enzyme can be modified. It can be phosphorylated. There is a kinase that phosphorylates it and turns it off. And there is a phosphatase that dephosphorylates it and turns it on. And when you think about what that means, okay, this hooks into the exact same networks as we saw for glycogen. So glucagon, low blood sugar, activates the kinase. What does that do? That flips this system over here. So now we are off. That means we are not going to make malonyl-CoA, and we are going to start burning fatty acids. So if blood sugar is low, you're going to start doing things like beta oxidation. If blood sugar is high, well, what are you going to do? You're going to activate this acetyl-CoA carboxylase, this ACC enzyme. That's going to start producing malonyl-CoA. That's going to inhibit beta oxidation, and it's going to start making lots of acetyl-CoA that can then be exported as triglycerides. So again, if your blood sugar is high, your liver cell is going to start exporting triglycerides. If your blood sugar is low, your liver cell is actually going to start consuming fatty acids as fuel. Okay, so let's review these signals really quickly. High citrate and or desphosphorylation, which is a signal from insulin, is a high energy state saying make malonyl-CoA. Ultimately, you're going to use that to say make fatty acids, synthesize fatty acids. On the other side, you've got a low citrate and or phosphorylation, which would be a glucagon signal. That's a low energy state that says slow malonyl-CoA production. And if you slow malonyl-CoA production, that says break down fatty acids because now you activate beta oxidation. And I'm just going to end with this slide here, which is maybe a lot to look at, but we'll zoom in and show this is the switch we just talked about. This is our, switch at acetyl-CoA carboxylase with fatty acid synthesis and breakdown. This is the switch we started with, the core of the glycogen switch. So we're seeing a switch between synthesizing and breaking down glycogen. And this is a switch that we talked about when we talked about glycolysis versus gluconeogenesis. Again, the same basic logic where you invert the logic. You basically have the same signal, in this case phosphorylation, that switches the whole logic of the system. And what I'd like you to start maybe appreciating, or hopefully you can appreciate looking at this, is that the same logic is just going to repeat over and over and over in metabolism. I could pull out other switches that have the same basic architecture, all driven by the same basic set of signals. What this means is something like insulin or something like glucagon, which is being secreted in your pancreas, can have a coordinated effect across cell types and a coordinated effect across metabolic pathways, which I think is pretty cool. Okay, so that's all I have on that. That was our bit on reciprocal regulation of fatty acid synthesis and breakdown. I've got one more video in this mini series, and in that we're going to talk about ketone bodies. Like what happens if you really run out of sugar and all you have around is fat as your fuel. So look forward to talking about that with you. Until then, I hope you have a wonderful time, and I will talk to you later.